Okay, so good evening everyone. Welcome to this last problem solving session of this course on compiler design, which is originally taught by Professor Santanu Chattopadhyay from IIT Kharagpur. I am Saurabh Sharma, PMRF scholar and PMRF TA for this course. So in week 12 there were some examples on intermediate code generation, and most of the things were covered regarding this only. So I have already covered. Okay, so let's wait for 2-3 more minutes. Let others to join. Then I will get started on this session. Good evening. Good evening. Good evening. So if there is any doubt regarding previous sessions, so you can ask using chat. I'm starting in 2-3 minutes. I'm waiting for some other students if they join. Okay, so maybe. So what I was telling that in week 12 it was totally dedicated for intermediate code generation, and in that mostly for the uh, problem solving part. There were most of the things covered. Those were examples of how to generate code for arrays, and how to generate code for conditional statements and other things, or color or query functions. And so I will first introduce the things which were taught using the slides of this week. Then I will solve the previous year questions, and if time will allow, because I have already covered all the things in previous lecture, so I will start from the very beginning, how compiler works, and I will just revise all the things from phase 1 of compiler to the intermediate code generation. That is all the things we have covered. I will try to wind up today with some gist of the previous lectures, and with the things which are taught basically on this week content. Okay, so let me share the screen. So first, I will start from the previous week's slides. So in previous week there were the things taught were three address instruction implementation. So there were quadruple representation and triple representation. Those were told. So in quadruple we have four things: two operands, one operation, and a destination. So in operation part, we actually provide the operation we want to perform on the operands, and the operands are the bit which indicate whether it is constant or pointer, and then there is the destination where we will store our results. So these are three things, four things which are actually stored. Then for each of the operation we will just create a new temporary variable or temporary location to store the result, and then we will perform the operation and place the result on that location. So why I am revising this, because I just want to let you know again what are the symbols. So E dot place is actually for holding the value uh, of E. E dot code actually sequence of 3 address statements corresponding to evaluation of. Okay. So next is so dot place is there for only means holding the value, and dot code is there for 3 address statements which will be performed. Like here, dot code is there for the code, and dot place is there for assigning the value new temp. Next is there is new temp that returns a unique new temporary variable. So for each of the storage area, we will just create a new temp. Then there is gen that accepts a string and produces it as a 3 address quadruple. And there is concatenation sign which actually concatenates to 3 address code segments. Like here, we have to perform the code, and then we have to, means we are first telling that we want to perform code on this, and based upon this we will actually perform this e dot place equal to e dot place plus e dot place. So this was the overall thing what we have to use. Now in this week content, the starting was from that transition rule of if then else statement. So if there is if and then something, so what we will do, we will actually backpass the true list with mquad, and then we will at next we will merge the false list with s1 dot next list. Similarly for if then else statement, so what we will do here, we will first take the true list of b and we will match with the m1. So if b will be true, we will go for an m1, and otherwise we will go for false list we will perform m2. That is the simple scheme. Then for next one we will merge the s1 dot next, and then s2 dot next. Then this is for code flow purpose, means once we will check the things, then we will go for next statement what we will perform later. Similarly for while and do statement, we will backfetch for uh, list for m1 dot quad. Then there is the begin L end. So this means we have the next of s will be replaced by next of L, means s is denoting the execution of L only. Then there is this derives a, so it tells for this the code generated will be s dot next list will be null. Then there is the L1 ms, so we will check for next comments, and then perform that backpatch with m dot 1, and all the things these are actually covered during the lecture, so I am not go deeper. I will just repeat from the solving part. So consider this is the example for there is a code which we will convert to a 3 address code. So how we will do, we will first check for this condition. So what I am writing, if a is greater than b, then we will go to somewhere. So then we will perform begin for this condition. When this condition will be true, we have to perform this block of code. is equal to y plus z, and then a is equal to a minus b. So y plus z we have to store somewhere. So we will create a new temporary variable and store that y plus z value to this t1, and then we will take this value of t1, and then we will place this value to x as a destination register. Sorry, destination. Then for a minus b, we will do the same, and then we will again uh, go to 1 to execute this instruction again. So if a is greater than b, then we will go like this. Then there will be another statement which we will perform when this condition will be done. So that is y minus z. So we have created this go to 3 for execution of loop. Till here we will go into the loop. Then when this loop is over, we will go to 8th statement like this. Go to 8. So 8 is telling t3 is equal to x. So we will store the value of t3 into x. I think something is missing here. Huh. Uh, we have to store first y minus z to t3, then we will store it to here. So one statement is missing. Okay. So in this way we will write a final code. Then if we write, if we want to write in a parse tree manner, so how we will create a tree? We will first start from S, which is the starting symbol that will provide begin, L and end. Then L will generate LMS. Likewise, till end we will go, and then we will parse it left to right, bottom top, and we will get M. Then we will perform A is greater than B. Then we will perform do. Likewise, we will take a value, then plus some value. So first value will be y, then z, and likewise we will create overall parse. For that same code, for this code, we can write each of the true list, false list, and the action using that code only. So what we will do for each of the code, we will perform any transition rule which is actually resulting this operation. Okay. Then there is for case statement. Uh, we there are some implementation alternatives. So linear search is for matching options, binary search for matching cases. There is a jump table. There is like then uh, there is a point that linear or binary search may cheaper if a number of cases are small. For large number of cases, we should go for jump. And in case if case value is not clustered closely together, jump may be too costly for space. So these are something we should take care of. Then there is jump table implementation. So this is all covered in the lectures. So here what we do, we actually take a code, we take a condition. So we let there are two values, maximum and minimum values. So we will apply condition on t, and then we will go to default case. So for any thing happens, we will go to jump table on t only. Means based upon value of t, we will switch the case. Then there are function calls. So it can be divided in two subsequences. First is calling, then return sequence. So calling sequence is there for set of actions that are executed at the time of calling function. Then return is for when we finish the function, there is what value we want to return, that is there for return sequence. Then there is for both some action performed by caller of the function and other by the calling function. So caller means which will call the function, and call is which is called. So like if you want to make it clear, so caller is responsible for evaluating the actual parameters. So it actually places actual uh, values where the callee wants, and then uh, there is some example. Then callee is for saving registers, then updating stack and frame pointers to accommodate m byte of uh, local storage, then corresponding the address is given. So caller is actually for calling a function, and callee is actually for uh, saving all the values. Okay. Then for return sequence, this was for calling sequence. Then there is for return sequence. What callee does? Callee actually places the return value where the caller wants, and then caller is there for save the value returned by call. So callee is here uh, placing the return value, and the caller is saving. So in calling, there is caller which is evaluating the actual parameters, and callee is saving the register, and then in case of return sequence, callee is placing the value, and caller is actually uh, saving the value returned by call. So there is function call. We can go like this. Then storage location for function. So value of n is not known until whole function has been processed. So we must know the value of n. Then there can be two possible solutions. We can generate final code in a list, and using pair of go-to statement we can also go. Then generating final code in list. So uh, we have to actually patch the appropriate instruction after processing the function body. So it is actually single phase code segmentation for Boolean expression, and control flow sequence, and maybe slow because it is going in sequence. So if we are using pair of go-to statement, we can go like this. For L1, we have some some code body, and for L2, we have some code body. So after going to L1, we will call going to L2, and sequentially it will be executed. So in concluding remarks, we can say that intermediate code is not actually mandatory, but it helps in retargeting compiler towards different architectures. So if we have different machines, and those are supporting some object code, we can generate using this intermediate code generation part. Then there is three address code and syntax directory schemes for three address code generation, and translation of almost all major programming language constructs have been carried out. So this was all which was taught during this lecture of week 12. Now we will go for the previous year questions. They're very less. So let's start with one previous year questions. So in first question, there was for a switch statement implemented as a jump table default cases. So there are four options. I want both of you can comment on comment section because it is taught in no, not in the middle of some table. Just read it carefully. Default cases. Uh, for default case, we actually go out of the table. So default case is not part of some table. Okay. So third question: if case values are widely spaced, it is better to use. So going for question 3. So in this, what we do if we have some uh, case, so we will jump for if we have some default case. So we want to come out of the loop or case. So that's why it is not a part of. Sorry for bad writing. So coming to question 3, if case values are widely spaced, it is better to use. So I just covered it just 2 3 minutes ago. So there were some alternatives we were going through. So in those, it was clear that if it is widely spaced, we should not go for jump table. So we should go for table search. So for third answer is A. Then it's a very simple one. Register saving is done by. Just comment your answer. Rename the pass. Just think and comment. No. Not for both. Uh, just remember there were two things. First was yeah, 6 also. So caller basically does the evaluation part and it is saved by calling. Then for each one, evaluation of actual parameter. Now it's very simple. I already told that evaluation of actual parameter is done by caller and register saving is done by calling. Okay, so here also A. We have till now all A's. Then two last questions because rest of the questions are repeated this uh, in this run, so I can't take those. So jump table is to table 4. Just answer this. Try to answer this. Uh, Jump table is suitable for large number of cases or any number of cases or small number of cases or none of the options. Because given in slides, it's large number of cases. If the cases are well spaced, uh, widely spaced, then we should go for table search, and if there are large number of cases, we should go for this jump table. Last one, backpatching is needed to generate intermediate code using 2 pass, single pass, multiple pass, or none of the options. For 10th one, just comment your answers. It's very simple. No, it's not 2 passes. I actually told we go by sequence. So sequentially we go with a single pass. Okay. So first something will be executed, then again next thing will be taken care of. Okay. So these are all questions from previous year. Now I will take from if there are some questions you have, you can just comment on the comment section. Otherwise, I will, as I have taken enough examples of intermediate code generation last week, so I will start from lexical analysis, some smaller questions, and I will come to this intermediate code generation as there are 1.5 hours left. So I will try to revise over all things starting from phase 1 up to the end of this. So I am waiting for 2 minutes if you have some. Okay. So am I audible now? Am I clearly audible? Okay. So I am telling that uh, just take your time, and if there are some questions based upon previous week runs, so you can ask those also. Otherwise, I will start over from week 1 content, and I will go to this week's content, taking some small examples. Major focus will be on this week's content only, but I will try to just revise the things which are taught from starting to end. So just taking 2 minutes. Till then, if you have something to add, you can ask in this chat box. Okay, so in the production rule, S derives L is equal to A. If L is given a single variable, then what is the value of L dot place? L is given a single variable. So what you are telling, something like S derives So in this case, the value of e dot place will be acquired by this. L dot place will be simply e dot place. Hmm. So if there is some value, if there is some variable, then there is a simple rule which is followed. You have to just take the value, take the yes, you have to take the value of s and sorry, value of the right hand side variable, and you have to put the value to the left hand side variable. So I can see just a second. Yeah, if you go to week 11 and slide number 4, so there is something like in first statement, if you see, there is s derives id is equal to e. So the code generated was, we put the uh, value of e dot place to id dot place, and same if we take that reference to e derives e1, so we will just put the value of e1 dot place to e dot place. So where there will be assignment, we have to just put the values of right hand side to the left hand side. Okay, is it clear? So just consider there is a uh, tree, there is a parse tree. So you will take some values as an identifier, what we write as id. So if there is id, so what we will do, we will just take that value of variable, like there is x plus y. So x value of x and y will be taken care by different ids or identifiers. So that value will be stored at id dot place. On next level, on upper level, when we will traverse, when we will what we say, we will reduce to the non-terminal. Then what will happen? Like there is e derives id, e derives id plus id. Say there is some rule, so that value will be stored to e dot place. Similarly, if there is something like L is equal to E, then that value will be reduced to L again. Okay, so ID will be reduced to E, E will be reduced to L. Likewise, we will reduce the value, we will take those values of ID to E, then from E to L. Okay, so yeah. um, I don't have any idea. Sir, can we expect more problems? Uh, Actually, PMRF TAs are there just for problem solving purposes. We are not even told about how the paper is set or how the exams will be conducted. We are just provided the previous year questions and some materials. We have to create the lectures and deliver it to you based upon just for problem solving, you can say. So we are not responsible, and we are not there for uh, means creating the paper. They are just for solving. Any other thing? And it is the NPTEL exam, so you can expect problems. Okay, so let me just revise the things. how we went from first day onwards, and many of the things you will already know, but it is the last one, so I want to just revise everything, make you revise everything. So if we start, just for compiler, we had uh, first pass is lexical analysis. Okay, so let me search for some questions if I have. Okay, so first is for lexical analysis. So in lexical analysis, what we do, we actually take some informal description of pattern, and then we actually create a sample keyboard generation implementation with this example. Okay, I will I will just let me go through one by one for each phase, or should I go for three code generation only? Okay, let me first I have taken this, so let me take the question for lexical analysis. It's very simple how we search for tokens, then I will go for this. So let there be some code written like this: total equals. Okay, am I not audible? Now am I audible? Hello, am I audible now? Okay, just write on chat. I will provide you some solution. Okay. Okay. So let's consider there is total is equal to count plus rate into 100. So how we just there is a simple kind of question which is asked, that how we have to uh, count the number of tokens. Okay, so tokens and number of tokens. If we want to just comment on this, then how we will check? So each of the variable or the value, we actually tell it as identifier. So these are identifiers. Again, if we have something like this, it is actually delimiter, and if there is something like this operators, so we can write it as operators. Okay, so if there is anything like this, one more thing, if there is something which is in inverted comma, those will be calculated as single token. Okay, something xyz is there in inverted comma, so that will be one token, and all these things are individually a token. Okay, so next what we have to do, uh, if there is uh, if we want number of tokens, we have to just add number of these 1 2 3 4 5 6 7 8, total 8 tokens are there. How we generate the tokens? Then there is lexemes, which is actually sequence of characters in source program that matches the pattern for a token, and what we say it identify by lexical analyzer for as an instance of that token. Okay, then token is actually the terminal symbol of the source language. Okay, so if we say token, it is a terminal symbol, and if we say lexeme, that is actually a pattern, uh, or we can say sequence of characters in that source programming language, which actually matches some pattern. Okay, and pattern is actually a rule that actually describes the all the lexemes that can be represented by that source language. So for example, if we say we have some tokens, we have some lexemes, and uh, if we want some pattern, uh, not pattern, it's we can say informal description of pattern. So how we will do, uh, like in like there is if, there is while token, there is relation token, there is id, there is number. Okay, so how we will go, lexeme is actually some pattern analyzer or sequence of character. So if lexeme is if, while, for this greater or equals blah blah blah, and there is some variable name, some or I or something, 0 to something, there is if, then while, then less than or equal to, or equals, or letter followed by digit or letter, or any numeric constant. So how it goes, there are some rules which we say patterns. So these are some rules, like there is a rule that letter followed by a digit, that will be a lexeme. So sample lexeme will be some variable name based upon this rule only. Okay, like count, there is some, there is someone we can write in C language. If we consider, based upon that we generate a token. Okay, so anything among these will be encountered by compiler, it will generate a token id. Okay, so there will be some rule, there will be some pattern based upon some rule, and based upon some pattern we will name some value, we will mark that value as a token which is actually predefined for each of the language. Okay, in this way we actually do the lexical analysis part. Now as you told, I am coming to first three address code generation part. Okay, so for three address code generation, okay, let's generate 3 address code for this one, this for statement. There is some statement given as I equal to 1, this or equal to n, then I plus plus. What we have to do, we can write within begin and end also, but I am just writing it simply. X is equal to a plus b into c, then it's done. Okay, so how we will do, I will just write till temporary variables, and based upon that, uh, for each of the temporary variable you have to just write the corresponding uh, cases, translation statements which are actually given in that NPTEL. Right? So how we will start, we should start from this initialization. Okay, so we are given I is equal to 1. Okay. Then in next step we will check for this condition. So if there is the condition I less or equal to n, then we have to go to somewhere sorry, then if it will be not fulfilled, means it is sorry, when it is done, then we have to go to somewhere else. Okay, so condition is done. Now what is inside the condition, we will write that, like there is this thing. So we have to go, if there is something written for precedence, we should go for precedence. If there is nothing given, we should follow precedence only, which is actually predetermined, like multiplication is given more priority than other operations, than addition, you can say here. So we will just write the code for this like this. We will just create a temporary variable t1, and we will store the value of b into c here. Then now we have this as t1, we have to add a here, and we will store it to t2. Okay, so t2 will be a plus t1. Then we have to store this value to x, so x will be equal to t2. We are done till here. Now we will perform this operation I plus plus, which actually means I is equal to I plus 1. Okay, and this will be continuously running. Okay, so we have to go to its initial position again, like we started from statement 2, so we will go to 2 only. Okay, so that so now we have to fill the values of go to statement, go to places. So go to places are like if I less or equal to n, we have to go to the execution initialization phase of, sorry, we have to go to the operations which are done when this condition is true. So that is starting from this fourth one. So we will write here go to 4. Then if it is done, we have to go to somewhere out of this statement. So we will create a new variable, sorry, new space. We will go to 9. There we will do nothing. So this way we write 3 address code for any of the for statement. Now if I want to write some translation rules for this. So uh, I will have to go through how the rules are there, if then else. Okay, so the first thing what I will do, I will just initialize the value of I. So I haven't written any grammar for this. Uh, so if we consider simple grammar which is given in the PPT and go through that only. So there is some grammar. Let me check. Okay, so we can go through this as grammar only, which is given in week 11 PPT and which is followed in throughout week 12. So I will not write the code fully. We will just start from that m dot quad is equal to 1. Then we will initiate the true list, and then code generated. So in one in true list, what we want to provide? We want to provide if I less or equal to n, then go to somewhere, and otherwise go to somewhere else. Okay, that is the thing. Then we will apply m dot quad again equal to 3. Now we will just apply e dot place now we will perform this one. E dot place is equal to b, e dot place is equal to c, and then we have to take some temporary variable to store the value, and then we will write the code generated. Code generated will be t1 equal to b into c. Likewise, you can take reference from slide 5. Likewise, we will generate overall thing. This is for one condition. Sorry, till one operation. Similarly, you will write for this. Now we have t1 e dot place, and we will write e dot place is equal to a, and we will just add it to t1, and then at last we will just write uh, m dot quad is equal to 4. There we will just update this value, and again we will generate the code, and then we will backpatch and go to the next list. So here I don't have a similar grammar, but I'm just trying to created with that while statement. So for and while are actually very close to each other. The grammar we are using for is we can use grammar of while with the for because both are same kind of loops. Uh, so if you want anything other than this in this C code generation part, can you write? So basic flow is you are given some code, some piece of code. You will just create three address code statement like this, where you will go step by step, and you will just start from initialization. Then you will check for condition, and then again you will go for uh, performing the operations which is there on true and false of that condition, and then based upon that just create you will just create the transition rules. Okay, these are the transition rules. And transition rules there are given those are given in the PPT. So for each of the statement you are writing here, you have to perform corresponding transition rule. You have to write that corresponding transition rule. Getting my point? Or anything other than this you want to know, just comment. Dev Prakash. So I told about the proper way of writing this. So anything more you want to know about this three address code generation? I have talked in three code generation. Means how you create it. Quadruple. Creation of quadruple. Okay, so that is very simple thing. Okay, so if you have something written for uh, creating the quadruple. Let me take one question of this. I have. So it's a very simple thing. Like I have given some examples like a plus b to c to the power d. Like there is something given like this. So how we will go? We just take the precedence. Okay. For very simplicity purpose, we can use precedence. If there is the precedence is not mentioned, then just uh, uh, consider the default one. Or there are some rules you can go through that how the productions are written. Those also provide some sense of precedence. Based upon precedence, uh, what is the basic rule? That power is given the highest precedence, then there is multiplication, then there is addition. Okay, so we will also go like this only. So we will take in quadruples what we have four things. We have operator, then operand 1, then operand 2, then there is result. Okay, so like here, if we want to write the code for this. So we will just go from highest precedence, that is c to the power t. Okay, so we will take two operands, one operator, and we will store the result somewhere in some temporary register or temporary variable. So we have taken some temporary variable, we have stored c to the power d, and then uh, now it is t1. Now we have to check for next precedence. There is b, so now we have b multiplied to t1. So we will provide another name t2, that is b multiplied by t1. Again there is now plus, so we will take t3, that is a plus t2. This way we can write it. That is the thing. So you can write in this way also. You can create a table for this, like you have operator, operand 1, operand 2, and result. So there is you can also write location. So in first location you have operator this, second location you have operator multiplication, in third you have operator like plus, then c, d, b, t1, a, t2, and the result is stored in t1, t2, and t3. Likewise, any other thing? So this will be just create. It's very simple thing, means you are given some expression. Okay, so you have to break it into the part where you will have at most one operator. Okay, if there is unary operator, say there is minus a, so what you will do for minus a, you will just take there will be operator in this one, and operand 1 will be a and operator 2 will be nothing. So we will not use operator 2 here, and we will store this value to say t4. Okay, so if it is unary operator, then also you will have operator, but you will not have any second operand. Okay, so this is rule for this, that you should have at most one operator. Okay, so there will be one more operator, that is mandatory. Okay, so this is for code generation. I told about lexical analysis. Then there is a major part which actually deals with syntax analysis. Let me take one simple example. Yeah, before that we should know about left recursion and left factoring. I saw some questions on discussion forum. These are not clear about what is left recursion and left factoring. So in left recursion, say uh, the part we are writing is like this, means the leftmost value of that right hand side derivation is actually the this one only. That's why if we will create a parse tree, what will happen, we can go like this: a alpha, a alpha, a alpha, and likewise. something will happen, then it will go for beta. This can happen. Okay, and so like every time A will call itself, and that will create a problem. So what we do, we actually want to eliminate this. To eliminate this, we actually uh, use this beta. So we write it as beta A dash, and where A dash will be epsilon or alpha A dash. Okay, so from here, if we are given any grammar like this, we will just perform based upon this only. So like there is example S0, S1, S or 0, 1. So here is S. Now what we will do, we will take A, this will be alpha, this will be beta. Okay, so how we will write it, we will just write S derives 0, 1, S dash. S dash will derive epsilon or 0s, 1s, S dash, likewise. Okay, so in this way we actually we try to eliminate the left recursion. Then there is another thing which is left factoring. So this is for left recursion. There is also a term called left factoring. In this, what happens? We have something like alpha beta 1, alpha beta 2, alpha beta 3. So whenever a parser goes for the grammar to generate some string, it gets confused whether it has to prefer this production or this production or this production, because the initials, the prefix of the uh, production are same. So what it does, or what we can do, is we can just take common. So we will take alpha common, we will write it like alpha A dash, and where A dash will derive beta 1 or beta 2 or beta 3. For example, if we are given something like S derives IETS, and there is IETSES or A, where E derives B. So how we can write it? We can just write it as S derives IETS IETS, then S dash. Okay, or A. Then S dash will derive epsilon or this thing. Okay, and then it derives B. Okay, so in this way we use we try to solve the left recursion problem and left factoring also. So then why we want to prevent this thing? Because top down bars sorry top down parcels, it creates problem. Then, take some questions on parser also if I have. So if there is some question regarding how to use parse tree to evaluate, so we can do it like this. For example, we are given some E derives E multiply T or T, then T derives T plus F or F, then that derives num. So from here we can write the semantic actions which can be performed using this. So E dot value will be E dot value, and write it as E1 dot value plus T dot value, then T dot value. For or we can write T dot value is equal to T dot value for this one. T dot value is equal to T dot value plus F dot value, and for this one T dot value is equal to F dot value, then F dot value is equal to num dot value. Now we have given something to evaluate. So there is given as 2 multiplied by 3 plus 5 multiplied by 6 plus 4. Okay. So what we are seeing here, first is both the operators this and this are left associative. Okay, so multiplication and plus are left associative. And second thing is that plus is actually after this multiplication. So here the precedence goes like this. So plus is having higher precedence. Now if we want to solve this, we will take first as plus as priority, and then we will go for multiplication. So there is two pluses, and it is actually left associative. So this is then plus then left one. So 2 multiply 3 plus 5 will be in bracket, multiply 6 plus 4 in bracket. Okay. Now so what we'll do, 2 multiply 8 plus multiply 10. Now it is left associative. So first we will go for this, then this. So 16 multiplied by 10, which will be 160. So in this way we can perform any operation using this parse tree, or you can say there is a grammar, using any grammar. Okay, so this is one thing. Now we are given some grammar, we have to go for um, I want to take some questions on LR0, LR1 items. Let me check. I have because I had done a lot of questions during uh, that respective week. So I think there is no more questions I have. I am taking just previous week question. I will just uh, making sure that we have. Let me check once more if I have anything in the question. Okay, so this is a common question I have for each of the compiler. I will just take this and then I will wind up. It will take a lot of time. So S derives AA, then A derives AA or B, so I have already solved it. Um, Previous year questions, we are actually provided with some link, but you can get it online by online searching only. We are not, you can go through the lectures. All the lectures I have covered the previous year questions, so that's not a problem. For each week lecture, I have done, um, I have first done the overall questions of previous years, just after revising the week content. So that is the source you can use, otherwise you can search them on internet. Okay, so if we want to go for LR0, SLR1, LALR1 and CLR1 for this only. So how we will do, we will first create augmented grammar. S dash derives S, then S derives AA, A derives AA or B, like this. Now we will write a pointer. We will start with this symbol, and it is non-terminal, so we will explore S. So S is having S derives dot AA. Now A is there, so A derives small a, capital A, and A derives small b. Okay, I have written it very bad shape. This is our I0. You can number it 1, 2, and 3. From I0, if we go for S, we will end it I1, and that is actually end of string. So there is nothing after this pointer. We can move for next one. Next literal is A. So S derives A dot A. Now A is there and pointer is before A. So what we will do? We will just take this A and we will explore its production. So A derives small a and A derives dot. This is I2. Then after small a, what will happen? A will derive A dot A. Now A is actually again non-terminal, so we have to explore it. Dot AA, and A derives dot B. This is I3. And if we will go for B, A derives B dot. It is end of string, so we have this I4. Now this is done. This is done. We have this one. On A, we will go to A dot. This is also done. I4, sorry, I5. On small a, what will happen? A dot A, and that will land up to this only on small a. And on small b, we will go to I4. Similarly, on capital A, we will go to A derives A dot. It is I6, and if we will start for small a, we will land up to here, and small b, we will go to b. Okay, now I think all are done. So next we will create the table. Okay, let me first check whether my solution is correct or not, otherwise we will do it again and again. That will be bad. Now we have total, yeah, we have total 6 states, sorry, 7 states from 0 to 7. Okay, that's fine. Now we have to create a table, transition table, which will have action and go to. So we'll have action and go to. So we have
action go to, and we should have states 0 1 2 3 4 5 6. There is the non-terminals S and A, and there is A, B, and dollar. So if we are in state 0 on 1, on on small a, we will shift to 3. Small a, we are shifting to 3. So S3 will be there. On small b, we are shifting to 4. So S4 will be there. On capital S, we are going to 1. On capital A, we are going to 2. Okay. We are at 1. If we will do nothing, we are on dollar, we will go to accept it. If we are on 2, there are 3 transitions. On capital A, we are going to S5. On capital B, sorry, no, it's wrong. On small a, we are going to 3, shifting to 3. On small b, we are shifting to 4. On capital S, we are not going anywhere, and on capital A, we are going to 5. Okay. If we are on 3, on small a, we are shifting to 3 only. Small b, we are going to 4, shifting to 4, and capital A, we are going to 6. Now, uh, 4, 5, 6. 4, 5, 6 are actually reduction states, because there the um, overall production is getting completed. So if we are on 4, A derives B dot. So we are at production number 3. So we will reduce using third production, R3, R3, R3 for LR0. Okay, LR0 parts. Then for 5, fifth is using this second one. So R2, 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 and sixth is using the first one. So R1, R1, R1. This is a simple LR0 parsing table for this. Okay, this way we create this parsing table for LR0. If we are going for SLR1, what we will do? We will just take that table, this table, and we will just write the reduction states in the follow of that symbol. Okay, so let me create it again. Action go to SA AB dollar states 0 1 2 3 4 5 6. S3 S4 5 6, sorry 1 2. At last, there are some reduction states which are remained.
There is some problem with device.
Okay.
So for reduction steps, we will use the follow of these non-terminals. So follow of S again. Follow of S. What is the follow of A? We have to calculate. So if we use this production, follow of S is from here. From first production, we have follow of S as dollar, and for second one, follow of A will be follow of S, and A is not followed by any non-terminal. So follow of A and follow of S both are dollar here. Okay. So the reduction steps we will write on the follow of symbols only. So reductions are there for R3, R2 and R1. All we will write in only follow of S and A. So for R3 and R2 we are writing for follow of A, and for this we are using follow of S. This is the overall thing. Okay, so this is for SLR1. A minute, let me reconnect the device. There is some problem. I'm not able to write properly. Just a minute. Now, so this is for SLR1 and LR0. Now we will go for CLR1 and LR1. So I'm not taking too much time. I'm just writing its canonical collection of LR1 item. So this will be like for I0. We have I'm just writing it from the solution. From here we will go for dot AA dollar. A derives dot small a, then A or B. A derives dot B. So what happens here? We actually take the first of A and dollar, and we will write the um, look ahead. Okay. S, we will go to S derives S dot dollar. 1, then A dot A derives dot small a capital A dollar. We should take care of look aheads here. Small a big one. Okay. So what I want to write. Let me share the solution to you. Will there's some problem with device. Let me share the handwritten solution. So like this. Uh, let's shared it earlier. So we just create a augmented grammar, and for uh, augmented grammar, what we do, we actually uh, use this okay. So we just create the augmented grammar, and for canonical set of LR1 items, what we do, we just start augmenting the productions, and if something is like this, uh, we take the closure of this, and for look ahead, we actually take the pointer and take the first of this, overall thing after pointer. Okay, so likewise we have created here. So first of this A will be first of something that is after this production. So first of this production is actually small a and capital A. So that will be small a only. And similarly, A is there, so B is also there. So first of A is actually A and B here. So we will write it like this. And one more thing we should take care of, that look ahead doesn't change when we make transition. Look ahead may change when we compute the closure. Okay, so each closure computation we will just take the first of the non-terminal we are using. Then for CLR1 we will go like this. We will start from 0. uh, for each of the CLR1 table, what we do, we actually take the action column, we take the go to column, and similarly for A, B and dollar and S and A, what we do, we just create a transition table which will have actually total 0 to 9, totally 10 states. uh, so in these 10 states, what we do, we just fill the entry based upon that canonical item. So all things will be same. Whenever we will shift from one state to other, we will write S3 as and then state. Then for go to, that is similar. We have to just take care of the states, and whenever there is reduction, we will reduce it using the follow of that production only. So I4 is, if we go to this fourth one, I4, we have A and B in look ahead. So we will reduce using third production, that is A dash B dot, and we will write the reduction entry on A and B only. So that is what we have done here. Okay, so on I4 we will have R3 on both A and B, and for similarly for I5 there is R1, and rest our entries are like that only. There is R3 in I7, and on R8 that is having A and B, so we create like this. Now if we want to create it for LALR1, what we will do, we will check for different entries, and those are having same kind of that uh, sorry, same transition but different look ahead. So we will just compile them both. So we will again, we will have action and go to, and we will have states. So there is A, B and dollar, and there is S and A. So I0, I2, sorry, I1 and I2 is there, but for I3 and 6 there are both similar things. So I3 and 6, if we see, so I3 is having same production as there is in I6, but there are different this look ahead. So we will combine them both. Okay, so we have combined them and we provide it as a new state having 3 6. The entries will be the entries in 3 union entries in 6. Okay, so we have written like this. So wherever we have used 3, we use 3 6. Wherever we have used 4, we will use 4 7, because 4 and 7 are having same case. Okay,
So the overall output we will get will be like this, that is given in the screen. Okay. So there is 3647, I5 and I6. Sorry, I9. 89 is also having same thing. So in this way we actually deal with LALR parser. And there may be shift reduce conflict, there may be reduce conflict. So shift reduce conflict happens when there is a table having shift and reduce entries together in the same cell, and for reduce conflict, the table having two reduces in same cell. So these two are actually conflicts which we can face during this. So this is all for the parsing part. So there is any question I can show you, because I'm not able to write. We have 10 more minutes, 13 minutes. So let me check if there is any question. Yeah, like here, we are given some grammar like this. E derives E plus T or T, then T derives TF and or F, then F derives F star or A or B. So in this case we just created LR0 table, sorry, LR0 transition diagram, and based upon this, these are simple steps. So when we fill the entries, we can see here at state 2 we have S4 and R2. So and there also, and state 9 we have S4 and R1 together. So that's why this is actually there is SR conflict, due to which it is not an R0 grammar. Okay. Similarly here we have reduce conflict. I have covered this example. I am just revising it for sake of perfectness. Uh, so there is R3 R4 there, so it is reduce conflict. That's why it is not LR0 grammar. Similarly here S10 and R5. And if we see for SLR1, there is no such example I have. So now coming to CLR and LLR1. So we have this thing. So if a grammar is CLR1, it may or may not be LLR1. So like there is a grammar, we have to check for whether it is CLR1 or LLR1 or not. So we have created a table. Now it is CLR1 grammar, no problem. So for LLR1 items, if we see state 5 and 9, so state 5 is this and 9 is this. So we have same state but having different lookaheads. Here lookahead is AC and it is CA. So what will happen if we will just create this, we will merge it, and that will be remain will be same as before. Okay, so if we create like this, what will happen? Data types d dot a or c. So 5 9 will having R5, R6, R6, R5. Okay, so 5 9 will have two kind of reductions. Okay, 596 and 61, 59 and 6. So there will be reduce conflict. That's why it will not be LLR 0, LLR 1. Sorry. Okay, just so simple. If we consider we have this 5 9 instead of 5 and 9. So 5 9 we will have R5 from here and R6 from here. So R5 and R6 will result in same cell. Similarly here also R5 and R6 will be on same cell. That's why there will be reduce conflict and it will not be considered as a LALR grammar. So that is all what I wanted to teach today. It is done from my side. So if you have any doubt, we have 7-8 minutes left. You can ask. So the lectures will be uploaded just after it. And many thanks for joining this handle pruning. Okay. Just so handle pruning means what kind of if we say about simple handle pruning. So what happens if there is something like there is written as ID plus ID into ID. Simple example. So ID is handle, and if there is some grammar like we are given some grammar in form of A derives ID. So what we do, we actually prune that handle. Uh, we actually reduce that production. Okay, so uh, what we say, it's actually removing the children of left hand side non-terminal from that parse tree, what we can say. Okay, so if we are given some derivation, uh, we are given some of the production, we will just prune it and we will uh, write the right side non-terminal. Is there any proper definition I can provide you? If we say about example, uh, So basically handle is the string part, you can say. Okay, so if there is e derives id, so id is and that id is there in some string we want to pass, so that is id plus id into id, like I told earlier. So first I will go through, we will take first id, so id will be handle there, we will just remove it and we will put that e on parse tree. So that is actually what we say as handle cloning. So simply if we say for proper definition, so definition will be removing the children of the left hand side non-terminal from the parse tree. Okay, so we have e derive id, so id will be on children side, e will be on top and id will be on its branch. Okay, so we will just remove id and we will just consider e there. That is in simple sentence. Okay, any other thing? You have 4 minutes more. Okay, another Evelyn, Jemima, if you have some doubt, some question, because it's last, there will be no further problem solving sessions. Thanks for joining, by the way, Prakash and Evelyn, and other ones was were joined and then left, and everyone who has joined this session and asked some questions or solved some answers. There was a guy named Revant and Mohammed Saf Faisal, they have joined, and also one guy Nikhil Gaur. You guys joined it thoroughly, and you both also today for today. So thanks a lot for joining, and hope you liked this session. So winding up this session, you may leave. There is 2 minutes left, in which I will just show the overall things I have covered. Then it will be over. Okay. So for 2 minutes, just this week's final revision, what is taught. So we started from translation rules. Translation rules are basically we are taking some three address code and based upon which what translation the machine will do and what translation we want to a machine will do, that will taken care of, that will be taken care of with the help of this translation rules. So these are some translation rules which is actually based upon the grammar which is taught in previous week. Then there was some example where we are actually checking this condition, and based upon the condition we are performing some operation, and then we are storing those values into some temporary variables and then to the source, like here to temporary variable t1 and then x. Then there is after execution of those statements we will go to some default statement which is out of control. Okay, we can create a tree also. Based upon tree we can write this these things also. So these are nothing but we are actually providing some values to these transition rules based upon this three address code and this parse tree. Then there are case statements where we thought that jump table may be costly for wide space and may be cheaper for too much a larger number of cases. Then there were function calls. There was callee and caller for calling sequence. It actually caller actually evaluate the parameters and callee save the registers. When there is return sequence, caller actually saves the return value by calling, and callee actually places the return value the caller wants. Then there was example function call storage allocation that is done after execution of function, and then there was
go to statement pair. So we go sequentially one by one. That may cause some of the uh, delay, but that is helpful. So that is all from my side. Thank you. Thanks a lot. Thank you. So hope we will meet somewhere. Otherwise, it was great taking this session. Thanks NPTEL for providing me such opportunity. Okay, ending this talk. Thanks a lot.